Okay, so this is chapter 13, homework number 1. And the first problem is an ore mixing operation with a bucket full of ore suspended on a bridge and is traveling 10 feet per second along when all of a sudden it's brought to a stop, and we're supposed to find the maximum horizontal distance that the bucket has swung. And to do this, we first need to figure out the kinetic energies, and that's T equals 1/2 mv squared. So T1 is 1/2 mv squared and T2 is 0 because velocity at the beginning is 0. Oh, sorry, the velocity when it stops is 0. After that, we need to find the work, and the work is from position 1 to 2 is negative WH. And if we, knowing that T1 plus the work is equal to T2, we can plug in our knowns and solve for h, which is the height, and we get h is equal to v squared over 2 times gravity. And if we plug in our knowns there, we get the height is 1.5 feet. And if we do some trig after that, we can find how far horizontally it's gone, which is 9.5 feet. All right, number 2, we have one truck enters a 2% uphill grade at 72 kilometers an hour, and it reaches a speed of 108 kilometers an hour in 30 meters. And we're supposed to find the average force on the wheels of the cab and the average force coupling between the cab and the trailer. The first, what we want to do is just change kilometers per hour to meters per second. We'll draw a free body diagram of the truck. And we'll want to find the kinetic energy in both positions. So T1 is 1/2 mv squared, T2 is 1/2 mv squared. We plug in our knowns for that, and we get 1.44 times 10 to the 6 Newton meters and 3.24 times 10 to the 6 Newton meters for position 1 and position 2. And then we'll want to find the work from position 1 to position 2 using this second equation. We'll plug in our knowns. We know that T1 plus the work is equal to T2, so we can plug in our knowns and solve for the force. And trying to find the average force coupling between the cab and the trailer, we need to know the kinetic energies of the cab and the trailer separately, so we'll find those. And then we'll find the work between point 1 and point 2 again, which is shown by this equation there. And knowing once again that T1 plus the work is equal to T2, we can solve for the force between the trailers. Alright, so number 3. There's a subway train that's traveling 30 miles an hour when the brakes are fully applied on the wheels of cars A, causing it to slide on the track, but they're not applied on the wheels of cars C or B. And we're supposed to find the distance required to bring the train to a stop and the force in each coupling. So first what we want to do is just find the kinetic energies, which is 1/2 mv squared. We can plug in our knowns for position 1, which would be about 7,800,000 pound-feet for the kinetic energy at point 1, and the kinetic energy at point 2 is 0 because it should be stopped. And we'll find our work between point 1 and 2, which is shown by this equation there. Negative force A plus force B times X. And plugging in our knowns, we can solve for the work from point 1 to point 2, which is negative 63,000 times X pounds-feet. And knowing that T1 plus U1 to T1 plus the work is equal to T2. And we can plug in our knowns and solve for X, getting 124 feet. And now we solve for the forces between A and B, which is very similar to what we just did. Find T1 for MB and MC. And T2 is 0 once again. Our work equation has changed slightly. It's the force between A and B times X minus force B plus force C times X. We'll plug in our knowns, and we should get this equation for work. And knowing that T1 plus work is equal to T2, we can solve for the force between A and B, and it's 19.3 kips. And then similarly, we'll do the same process, but for the force between B and C. And we can solve for the force between B and C, which is 8.6 kips. Alright, so this one, a sphere is given a downward velocity of 5 meters per second, and we're supposed to determine the angle at which the rope will break, knowing that it would withstand a maximum tension equal to twice the weight of the sphere. So once again, we'll want to find the kinetic energies. 1/2 mv squared. So T1 is 1/2 m times 5 squared. We'll get the kinetic energy is 12.5 meters. And T2 is just 1/2 mv squared. We don't know any of those variables yet. We do know the work is mg times 2 sine theta. And knowing that T1 plus the work is equal to T2, we can plug in our knowns and solve for V. We'll also need to sum the forces in the x direction, which is negative 2 mg. When it breaks, is negative 2 mg minus mg sine theta equals ma. We know that a is v squared over 2. We can use these two equations to solve for v. Then we'll plug in v. And then we can solve for the angle at which it should break. Number 5. So there's a chairlift going up like a ski lift going up a mountain. We know that it needs to transport 1,000 skiers per hour. Average speed of the lift is 75 meters per minute. We're supposed to find the average power required and the average capacity of the motor if the mechanical efficiency is 85%. and if a 300% overload is to be allowed. So we know the work can be summed up as N times mgh, and since we know the number of the people, the mass of the average person, and gravity and the height they're supposed to traverse, we can come up with the work needed. And the power average is just the work divided by the time. We know the work and we know the time, so we can get 57.2 kilowatts. And the capacity should just be the max power over its efficiency. Since the max power is a 300% overload is to be allowed, so the max power should be 229. We just divide that by 0.85 and we get 269 kilowatts. Should be the capacity. Alright, 6. Number 6, we have a 2 kilogram collar is attached to a spring that slides without friction in a vertical plane along a curved rod. We're supposed to find its velocity as it passes through point B and as it reaches point C. So EA is equal to the length from position OA minus the length from position OC. We can just plug in and get EA is equal to 100 millimeters. EB is equal to the length at position B minus the length of position A. Plug in and get EB is 50 millimeters. And at EC, 0 millimeters. Using VA is equal to 1/2 K times E squared, we can plug in and find that VA is equal to 3 joules. VB is 1/2 K E squared. We can plug in and solve for VB is 0.75 joules and VC is obviously 0 joules. Knowing that TA is 1/2 mv squared, and TB is 1/2 mv squared, TC is also 1/2 mv squared, we can plug in the ones we know and solve for VA and VC, which are equal to 0, and VB is equal to negative 3.924 joules. And knowing that, also we know that TA plus VA plus VAG is equal to TB plus VB plus VBG. We can plug in our knowns. We get that VB is 2.48 meters per second. And using a similar method, we can find that VC is equal to 1.732 meters per second. And number 7. Number 7, we have a box that's falling towards a spring on a 20% incline. And we're supposed to find the maximum force, the maximum deformation of the spring in the spring after the package is brought to a rest. So we know that T1 plus V1 is equal to T2 plus V2. We know that T1 is 1/2 mv squared. We can solve for that, get 100 joules. We know that V1 is mgh plus 1/2 ke squared. And we can plug in our knowns and solve for V1 is equal to 1,379. We know that T2 is 0. We can solve for V2 in a similar manner to V1, except this time with an unknown. And we can use all this to combine and solve for x, which is 0.269 meters. Number 8. We have another truck. This time it's going up a 15% incline. We're supposed to find the magnitude of the brake force and the additional time required to stop the truck going up the hill, neglecting air and rolling resistance. So first we'll just draw a simple free body diagram. And we know the impulse momentum equation, mvo plus sum of the impulse from position 1 to 2 is equal to mv1. So we can plug in most of our knowns here, and knowing that W is equal to 20,000 pounds, we can finish the rest and solve for the force, which should be 2,280 pounds. And using that in a similar equation, we could plug in for the force, and we solve for T. And we get T is equal to 9 seconds, and 9 minus 6 is 3 seconds. Number 9. So we have a pulley system that is under 150 newtons of force. We're supposed to determine the time at which the velocity of color B will be 2.5 meters per second to the left, and the corresponding tension in the cable at that time. So just looking at the cable system, we know that XA equals 2YB and VA equals 2VB. Now if we draw a free body diagram of position B and sum the forces in the x direction, we get 2T minus 150 newtons. And the sum of the impulses is equal to the sum of the forces times T, which is 2T minus 150 newtons times time. And then using this second equation here, we can plug in our knowns and get 2T times time minus 150 times time equals 20. And then we'll do a free body diagram of block A and sum the forces in the y direction and get T minus 29.43. And then the sum of the impulses of A is equal to the sum of the forces times time, which is T minus 29.43 times time. Using a similar equation to the one above, we can plug in for our knowns and get that T is equal to 0.54 seconds. And using a similar equation, we just plug in and find that the tension in the ropes at the same time is 56.8. All right, number 10. We have a bullet shot at a block connected to a string. And then block swings to a maximum angle of 60 degrees. We're supposed to determine the initial speed of the bullet, the impulse imparted from the bullet on the block, and the force on the cord immediately after impact. So we know that the initial potential energy of the system is 0 because nothing's happened yet. T1 is equal to 1/2 mv squared. If we draw a free body diagram of the system, we can solve Vg at position 2 is equal to mg 1 minus 1 cosine, L minus L cosine theta. T1 is equal to Vg2, and T1 is also equal to 1/2 mv squared. So 1/2 mv squared is equal to Vg2. We can plug in our knowns and get that V is equal to 4.65 meters per second. We know that MVO plus MV1 is equal to MV. So we can plug in our knowns there and get that the initial velocity is 779.65 meters per second. Now if we solve for the bullet instead of the block, and knowing that MVO minus force times time equals MV, we can plug in our knowns and solve for the momentum. For the impulse, which is 4.649 joules. And if we sum the forces in the y direction of the bullet, we can solve for the force, plugging in our knowns. Oops. All right, number 11. There's 3 steel spheres of equal mass, and they're suspended from the ceiling by cords. And we are supposed to determine the velocities of A and B immediately after the first collision, and the velocity of B and C immediately after the second collision. So if we do a free body diagram of the steel balls, we'll figure out that MVA plus MVB is equal to MVA prime plus MVB prime, because we know that the total momentum is conserved. We also know that V naught is equal to V prime A plus VB. Then we can solve for the relative velocities. We know that V prime B minus VA prime is equal to E times VA minus VB. Along with that, V prime B and V prime minus V prime A is equal to V naught times E. Solving for V prime A and V prime B, we get these two equations. And for the second hit, we know that the momentum is also conserved here, so MVB prime plus MVC is equal to MVB double prime plus MVC prime. And the relative velocities at the second point are VB prime minus 0 times E is equal to VC prime minus VB double prime. And we'll plug in our knowns and plug in our knowns to those two equations, which would just be VB prime at this point. And we'll get these two equations. And then using those two equations, we can solve for VB double prime and VC, which are shown there. All right, and number 12. We have a 1 kilogram block. It's moving with a velocity of VO is equal to 2 meters per second, and it hits a 5 kilogram sphere, which is at rest hanging from a cord. And we're supposed to determine the maximum height reached by the sphere and the distance traveled by the block. So if we do a free body diagram of the instant when the block hits the sphere, and we know that momentum is conserved, we can come up with this first equation here. We can plug in all our knowns. We can solve for the velocity of b, which is 2 minus 0.5 VA, velocity of A. And we know that E is equal to the velocity of B minus velocity A over the work of A minus the work of B. So we can plug in our knowns here and solve for VA, which would give us 2.4 meters per second. And since we know that VA is 2.4 meters per second, we can plug that into the equation for VB and solve for VB, which is 0.8 meters per second. And we know that T1 plus V1 is equal to T2 plus V2. So we can, knowing that, we can solve for H. And if we plug in our knowns, we can get H is equal to 0.294 meters. After that, we can do a free body diagram of the block, and we know that T1 plus the work is equal to T2. So plugging in our knowns there, we can solve that the block went 54.4 millimeters.